No? Hello, welcome again to this IFIMAC Day. We will have two more talks before lunch. Let me remind you that we are all invited to have lunch at the Plaza Mayor building, okay, at 1:30. So we expect all of you to be there. Then we will have, as I told you, two more talks regarding two collaborative projects. One of them that is currently running, the one that Juan Aragonés will tell us about, and the other one that was already finished, the one that Pablo Ares will tell us about. And before going on, I just wanted to share with you two thoughts that I had during the talks of this morning. We saw two talks, one regarding a project that was already finished, and that for me is an example of a success of a collaborative project at IFIMAC. Probably the younger researchers don't know that one of the requirements to ask for one of these projects is to not have a past collaboration with the other groups that you join in order to apply for these projects. So this was one of the big bets of IFIMAC in order to invest this Maria de Maeztu program. And we saw how Nicolás didn't have any interaction with the group of Juan Carlos Cuevas, and they're right now running a coordinated project all together. So this is a success story. It will be, I hope, the same for the case of Juanjo Palacios, and let's see what we have here. And the other thing that I thought this morning, and I didn't say to you, is that in contrast to what we have in an international conference where we usually go and just tell about results, here we saw how science is usually difficult. We saw that in the project of Juanjo, they had problems with the radiation. They didn't reach the results that they wanted yet. We saw how also Nicolás had problems developing these thermal power measurements. And this is something very common, and I would say it's part of the fingerprint of IFIMAC, in which we work really in the frontiers of knowledge. So success is difficult, and in the way to success, we usually cross a few times. And this is something that I think we can share here and not in an international conference. And this is special for the young students. And that's something that we have to transmit to young researchers also. And this is a good platform for that. So, Juan Luis, he will tell us about a project that is running, and it's entitled Dynamically Driving Spinning Colloidal Particles of 2D Lattices, a topological active metamaterial.
Thank you. So, first of all, I would like to thank the IFIMAC for the opportunity of undertake this collaborative project. It has been an interesting adventure. And what I tried with this project was to become one of you, because yes, I do soft matter. So let's address the elephant in the room. What is soft matter? So soft matter is condensed matter with densities that range between a liquid and a solid. So it's condensed matter. And what makes soft matter very particularly interesting for me is that the interaction energies between the elements of the material are of the order of KBT. So are always in the dynamical changes. And that's what we try to do all the time. So with that said, let's move to this idea, because it's an ongoing project, and we don't have that much results yet, but I'm going to give you a brief overview of this project. So I've organized this talk in a soft manner. It's not a canonical talk in the sense that it's a project that is ongoing. We don't have that much results yet. So I've organized it in 5 different questions that I'm going to try to answer during these minutes. So first, I will introduce the team, answering where do we come from. Then I will try to explain the motivation and objective of this project, answering what do we want to achieve. Then, how are we going to do it? Where we are, the preliminary results that we already have, and where are we going? What are the future plans for this project? So, a very quick and brief introduction of the team. On one side, there is my group with Laura's group. We serve the same group, and we are focused on soft matter and material engineering. So we develop soft materials and characterize its properties. Laura is an expert in vesicles and interfacial mechanical properties. So she developed this kind of vesicular materials where we can put polymers inside and phase separate when subjected to osmotic stresses. We also can control what we put inside this vesicle. In this case, we put, the video is not running, I don't know why, but this will be rotating inside the vesicle. And we are also studying how colloidal particles translate in complex environments. And in particular, we are very interested in tribology or friction at mesoscopic scale. This is one leg of the team. The other leg is the group of José Vicente Álvarez, who in recent years has been working on topological properties of mechanical materials. So his contribution to this project is going to be crucial because I know very little about topology. It's not my field of expertise, so José Vicente is helping us with this part to define the topological spaces that we find in our system. And also, we have the group of Salvatore Asenza, who is focused now on mechanical properties of biopolymers, but he has been working on diffusion in a structural environment. So, and he came from the coarse-graining modeling community, which when you are dealing with complex systems, is not only nice to have, it's a must-have in your team because allow you to identify the critical physics of the system. So, with that introduction of the team, I'm going to tell you about our motivation to undertake this project. As I told you, we are really into the transport of colloidal particles in complex and structural environments. For example, I am really intrigued about how cells move in tissue like material or the extracellular matrix. I would like to extract the general rules that allow this type of movements. We are also very interested in how we can exploit the environment to control collective behaviors. For example, in bacteria, here you have bacteria moving a ratchet. So in principle, you can extract work from a bacterial bath, or you can use it to control the transport of crowds. In fact, this is very nice work from Iker Surigel. And now, when they are building new stadiums, they put these pillars in front of the exit doors to control how crowds must escape in case of an emergency. But on top of this curiosity about how this system behaves, this has important technological applications, for example, to develop techniques for particle separation, or as I told you, to control crowds. So this is our motivation. We want to study transport of colloidal particles in complex environments. But what's the main idea that we want to tackle? Well, our inspirations come from topological insulators. I'm going to fly by this because this is, I know very little about this compared with any of you. So the idea is that if you have a topological insulator and you apply a strong external magnetic field, the electrons feel this magnetic field and start orbiting because of the magnetic field. So if these electrons are in the bulk, they perform these orbital trajectories and are localized. So in the bulk, this system behaves as an insulator. But on the edges of the material, the electron reaches the boundaries, so they don't complete the orbital trajectories, and therefore they are not localized. They translate along these edges. So it's conducting in the surface of the material. And these are called the surface states. For me, more interesting than the topological insulator itself are the Floquet topological insulators, which exhibit the same properties, but instead of applying a static magnetic field, they apply a time-dependent magnetic field to obtain this kind of behavior. And as I will show you shortly, this is what we have in mind with our colloidal system. But importantly, this behavior is not due to the quantum nature of the system. It's due to the topology of the band structure. So if we can replicate a system we share common topological structures to those exhibited in this system, we can achieve this type of structure. So, and this type of transport is really interesting from the transport point of view because in these superconducting materials is dissipation. So if we can achieve this kind of transport, we will be very efficient in our system. But sadly, we are not the first one thinking about this. In fact, the group of Thomas Fisher has developed this really tough colloidal system in which they print these ferromagnetic patterns and then put a paramagnetic particle on top and then apply an oscillating magnetic field, and the particles translate through this pattern. And they have shown that they observe close trajectories in the bulk and translating trajectories at the edges, resembling the behavior of a topological insulator. And they have done it, and they have described all the topology of the system. It's a really nice work, but the system is really, really, really complex. So can we make it simple? I like simple. There are also another system using active matter. In fact, they use self-propelled particles, but this is a pure theoretical work. They just break the time reversal symmetry with the geometry of these annular channels, and they achieve these density waves that propagate unidirectionally along the edge of the line. They publish Nature Physics paper, and they have really good fun, but try to do it in experiment. So, can we do it simple than this? So, we are trying. Our idea is to use the simple system that I can came up, which is a spinning particle inside of an ordered array of obstacles. And I'm going to try to show you, if I how we can obtain a material with transport properties similar to those of topological insulator. Starting with a rotating particle in an unbounded fluid, this is just rotating around the axis perpendicular to the screen. It just rotates in place with experience any translation, right? It just dissipates all the energy in the fluid flows generated on the fluid. This can be described by the Navier-Stokes equation, that if we neglect all the inertial terms, this means these left terms of the equation, we can arrive to the Stokes solutions, which tell us that these velocity fields are proportional to the angular velocity of the rotating particle, and inversely proportional to the square distance to the spinner surface. Okay, what happens if I put this spinner close to an obstacle? That's what we did. We ran simulations in which we solved explicitly the fluid using a lattice Boltzmann fluid. We put a fixed particle at the center and a spinning particle at a distance of about particles diameter. And as you can see here, these particles perform this orbiting trajectory around the obstacle, more like a spiral trajectory. And we measure the translational velocity of the particle along the tangential direction and the normal direction. You can show here in blue the tangential velocity of the particle, and in orange the normal velocity. You can see that the particle moving away goes slowly up to 0, and then reaches a steady point where the particle just stays at the same distance of the obstacle orbiting around it. And obviously, the velocity, the tangential velocity of the spinner, depends on the distance to the obstacle. So, can we? How we can describe using the hydrodynamics this behavior? First of all, we have our obstacle or rotating particle. The rotating particle generates a velocity, a rotational flow that reaches the obstacle, and then transfers its momentum to the obstacle. But since this obstacle is fixed in place, it must exert an opposite force on the fluid for the momentum to be conserved, right? So, in return, this obstacle is generating a Stokesless flow, which reaches the spinning particle. And this is the responsible velocity field of this particle orbiting the obstacle, right? So we have now why this particle is orbiting around an obstacle. But what about the spinner moving away from the obstacle? The only thing that I came out with was an inertial effect. Although the range of numbers is really small, between 10 to the minus 3 and 10 to the minus 1, I think that there are inertial effects in this system. So, can I explain the repulsion between the obstacle and the spinner with a lead force, like let's say the Magnus force? I don't know if you are familiar with Magnus forces and lead forces. For example, have you seen the Roberto Carlos goals in the 2004 World Cup? This goal that made this huge turn. This behavior is it's an inertial effect, and it's called a Magnus force that happens when you have a translating particle suspended on a fluid that at the same time is rotating. So this exerts a lead force that moves the particle in the direction perpendicular to the translating direction. So this Magnus force decays with the cube distance to the obstacle, as we were seeing in our simulations. It decays with the cube distance to the obstacle. So maybe this can be the repulsion force between the obstacle and the spin. So obviously it's going to depend on the translational velocity and the angular velocity of the spin. So far so good. We have a particle that hydrodynamically interacts with an obstacle, and it do these orbiting trajectories, and we can control if we want to move it far away from the obstacle just by increasing the angular velocity. But this is boring. We can put some more hot sauce here. What happens if we functionalize the obstacle and the particle? For example, I can put some carboxylic groups on the surface of my particle, and if I control the pH, I can get negative charges on my spinner, and at the same time, I can use some polyelectrolyte, cationic polyelectrolyte, to functionalize the obstacle. So now, on top of the hydrodynamic interaction between the obstacle and the spinner, I will have a screen Coulomb interaction. So in this dimensional force field, where I put all the dimensions in these three parameters, alpha, beta, and gamma, and I assume inverse square dependence for this Coulombic interaction, now I can control the distance between the spinner and the obstacles with the rotational frequency of the spinner. So let's see what happens when I put this system with another array of obstacles. Sorry. Let's start with a square lattice of obstacles. Here we have our four obstacles, and depending on the angular velocity of the spinner, I will have two different trajectories. If the angular velocity is lower than a critical frequency, so there is no hydrodynamic repulsion between the obstacle and the spinner, the particle, and therefore the attraction, the Coulombic attraction dominates the system, the particles will perform these closed loop trajectories orbiting around the obstacle. But if I increase the angular velocity of my spinner above that threshold, then it will reach this closed trajectory around the four posts of the lattice. So we call this orange trajectory an inner state, which is dominated by the hydrodynamic repulsion, and this closed trajectory, a corner state that will be dominated by the Coulombic attraction. So, and we can switch between one another. That's why we are thinking about a topological space in this system. One will be winding number 1, and the other one will have a winding number of 0. But as I told you, this is an ongoing work. This is just an idea of what can be happening. So now I can change the frequency dynamically in a time-dependent manner to control if the spinner is in this trajectory or in this. So that's what we did. This is my time-dependent frequency, the rotational frequency of the spinner. And if I match this exact frequency, where my particle starts here, is performing this closed trajectory, then I increase the angular frequency, so repulsion dominates, my particle jumps to the other trajectory, stays there until the frequency is reduced enough for the particle feel the Coulombic attraction to this other post, move with this other post, and so forth and so on. So I can achieve this type of trajectory in which the particles move ballistically along one direction. We can play with the frequency and the sense of rotation of the particles, so we can control, we can derive the spinner along any direction in the lattice. We have other frequencies for what we observe close trajectories. It will be a bulk state. There is no ballistic transport at the long length scales. But this is all from the computational point of view. How are we going to do it in the experiment? Well, we already have this set up the lab to generate homogeneous rotating magnetic fields coupled to a microscope, so we already have the spinners. We are dealing with this part because we want to precisely control how we print these arrays of force, this lattice of obstacles, and we are going to use BEMS soft lithography, which is not in place. We need throughput. We need a bunch of equipment that here is always hard to get. So we are dealing with this, but in the meantime, we can create posts in a disordered manner using particles that are stacked on a substrate. That's what we did. We stacked these particles and we put our spinors in these lattices. And what we see is that they translate through these disordered lattices. And we observe two main behaviors. And this is really interesting for me. Seems like these particles migrate towards regions with more dense, to regions with more obstacles, more dense regions. And then they get trapped there. When they find some obstacles in a kind of order arrangement, they just stay there. This is something that I would like to study. We also see that the ballistic transport is transport in this one, sorry, that it just crossed the entire window of view. This ballistic transport depends on the density of the obstacles and also the order of the obstacles. So for this, it would be very nice to have the soft lithography where we can control the noise that we put on the lattice positions of our lattices. So let me finish with the things that I would like to study in this project. First, these things that I just told you about this disorder-induced transport, because if I have this, take into account that this experiment that I just showed you, the frequency is constant. So what will happen if I put a time-dependent frequency on the spinor? That's something that I definitely want to do when we have the software lithography on site. But in the meantime, I would like to study this disorder-induced transport. Everything is similar to what Pablo Ares was telling in the first talk, about in a completely different system. And also study this directive motion that we see on this going towards a more dense region. So I think that I'm going to left it here. So thank you very much.
We have time for some questions, comments. Maybe we can.
Thank you for this nice talk. I'm wondering, topology is something associated with quantum mechanics, and well, in topological insulation.
But there are tons of examples of topological mechanical systems.
Yeah, but they're waves.
They are waves. Is it?
What are the waves?
By the way,
Where are the waves in what you do?
there are some waves in the fluid, right? But there is no density fluctuations, right?
Coriolis force is a topological effect.
Yeah, I know you said you're an expert on this, but what is the parameter that controls the non-trivial topology and from the trivial one?
I'm not an expert. In fact, if you realize we obtain this ballistic transport, but it's not at the edge of the material, right? We observe it in fast. So is this topology or not? This is something that I would like to explore, and I don't have the answer yet. So yeah, this is something that we are getting.
A very nice setup. My question is, when you add more particles and you want to make a large transfer of particles, then the whole idea might break because of interaction between particles. Is that could be an effect, a non-trivial effect, and as strong as the obstacles. Actually.
Yeah, totally agree. But instead of killing the effect, maybe you enhance it because you are creating this.
No, because they are rotating, so it's difficult to know.
Yeah,
that's something to be checked.
And the rotation in a lattice, in another lattice.
I mean, if you push divide those with the cushion. That if you rotate, I don't know if you have the same effect. Maybe it's a repulsion. I don't know. That's something to
But
check.
they are rotating and translating. So
Yes. Who wins? That's the question.
yeah. Yeah, they rotate in the same direction.
Yes.
Yeah, indeed, they repel each other. If you find two of them, they repel each other. But that's in the absence of dipole-dipole interactions. But these are magnetic particles, so. But we have ways to kill the magnetic interaction.
There are lots of effects to us.
Yeah.
One more question? You have time for one more?
Thank you very much. I wanted to ask you, when you have the ballistic movement, that's because you always, because you choose the proper time to change the frequency. If you don't do that and you have effect of thermal fluctuations, would you have something like a random walk between all these same circles?
Yeah, that's something that we are working on, and that's really interesting because depending on the so we are at infinite Beckler number, right? We don't have thermal fluctuations, but I think that this is robust enough. If these are topological transport, that's the idea. If this is a topology driven, we should get rid of the thermal fluctuations because maybe you jump from one row to another, but then you engage in this row again. So at the end, you will end up with ballistic transport, at least in one direction.
Okay, I think we have to move to the next talk. Thank you very much. Okay, now we will have Pablo Ares that is going to talk about collaborative project that already finished, I think a year ago, and it's entitled Ultra-High Pressure Chemistry at the Nanoscale.
Thanks, Christina, for the introduction. So I will talk about the results on this collaborative project titled Ultra-High Pressure Chemistry at the Nanoscale. That was one of the first round collaborative projects, I think. So first of all, I want to give some facts on the project. So basically, the participants, and acknowledge all of them, they were like divided into three main groups by three main PIs, Julio Gomez, Fernando Martín, and Enrique García Michel. I think we were able to gather quite a equilibrated team. So we have a group expert in scanning probes and 3D materials, then the group of Fernando, expert in BFT and simulations in surfaces and also 2D materials, and the group of Enrique García Michel with a lot of expertise in photoemission and spectroscopy measurements. Also, there were some more people involved, not from IFIMAC or UAM. In particular, I want to thank Adolfo del Campo from the Dinamically video, who is the technician for the Raman measurements, who is always very helpful, and for these measurements, he helped a lot. And also the Electra synchrotron in Trieste, because we went there to this ESCA microscopy beam line, and they were also very helpful, and it was a total experience. And it's for Julia and me, that was the first time that went to a synchrotron, was quite an experience. So, just some of us, the main outputs of this project were these two peer-reviewed publications in these two journals, but also an outreach publication that we were invited by the outreach journal Imaging Microscopy, that they saw our results on electronic properties by tuning them with ultra-high pressure, and they invited us to submit a publication. Okay, so then after this, some, let's say, facts of the project, I will talk about different things. First, I will introduce the motivation for this. Then I will just talk about science on the different results we obtained, and I will finish with some long-term implications of this project. Okay, so just introducing this. If we take a look to the ranges of pressure in nature, we see it spans quite a lot of pressure range, from vacuum in intergalactic space to, let's say, the high vacuum, for example, we know about from our labs. pressure at atmospheric level, 10 to the 5 pascals, which is the pressure we are used to live. We know it very well. But then if we go increasing the pressure, for example, deep in the ocean, on the center of planets, center of stars, pressure can go up very high order of magnitude. Here it's important to notice what is the maximum pressure we can achieve in laboratory conditions, and this is basically around 1 terapascal. And this is achieved with special diamond ambient cells that consist in two opposing diamonds very sharp. We put our sample in the middle, and then by applying forces, we can exert very high pressures. Okay? What happens now if we look at an atomic force microscope with a diamond tip? We can see it as a nanotechnology version of one of these diamond ambient cells. You see, if we see the pressure at the force over the area, considering our tip radius, which is very small, with moderate forces, we can apply very high pressures. We can estimate that, and we can reach an expression where we directly can relate the pressures with the force. So by controlling the force, that's something we can do very well with an atomic force microscope. We can control very precisely the pressure. And now, if we go back to these pressure ranges, what is the maximum pressure we can achieve with this approach? By just taking into account a standard AFM and a standard commercial AFM probes with diamond tips, we can estimate that we can achieve pressures of the order of 300 gigapascals, which is really close to this highest pressure in laboratory conditions, but with the added value that we just need an AFM and commercial probes. Nothing very complicated, just simple stuff. Okay, so once we realize that, we said, okay, where we can apply these pressures. Immediately, graphene came to our mind. We were working with graphene in the laboratory, and it has, all of you know, many remarkable properties, including very good mechanical properties. So it was our first candidate to apply ultra high pressures. But also, apart from these good properties, there is interest in tuning graphene properties for other applications. So we want to use this ultra high pressure approach to try to tune properties of graphene, and this is what I will show next in the talk. So in our experiments, we use mechanical isolated graphene, which is the highest quality one, almost has no defects. So we can see them in optical microscope. These, let's say, with lower contrast area are single layer graphene areas that we can check with Raman spectroscopy that it's indeed single layer graphene, because you see these two characteristics in Raman of graphene. Is that this is single layer graphene, high quality, because also there is a D-peak, which is because it's not present here, which is the peak accounting for defects. So it's telling us that our graphene was very high quality. Okay, so after this introduction, I will show you our results on tuning the properties of graphene. And first of all, I will start with tuning the electronic properties of graphene. And this is the results in here. So the approach we follow was the following. We have our tip in AFM working in a mode, typically called dynamic mode or tapping mode. The tip is oscillating far from the surface, so we are not putting pressure on it. So with this, we can just visualize our sample. This is just a part of a graphene sheet. And now when we go to modify, we just bring the tip into contact, put a pressure set point, and now we can scan the tip at this pressure in a given area. When we finish that, we bring the tip up back to this tapping mode, and we see the effects. And we can see that this area has flattened and has sunk, and we have modified it with this pressure. We can do this at different ultra high pressures. We see tens of gigapascals, and we can see as we increase the pressure, for example, here 13 or 16 gigapascals, there are no modifications, but as we increase the pressure 20, 25, 39, and so on, the areas appear more modified, and at 40 gigapascals, the graphene sheet broke, and we just put the silicon dioxide on the substrate, and material came out, and I mean, we just finished here. But if we now take a look to these areas, we can see that the distance we have sunk it, I mean, the distance we have get the graphene closer to the silicon oxide can be controlled precisely with the pressure we apply. So in this way, we can control very precise the graphene coupling with the substrate. But it is known that the degree of graphene coupling with the substrate also is affecting the level of doping. So in order to study what is the level of doping in those areas, we brought our samples to a micro-Raman facility, the one here in Dinamically video, and we took a spectra. I mean, the spot in that Raman is like 200 to 300 nanometers, so we can take a spectra at very precise locations and even take maps. So if we take a spectra in each of the modified areas, we can see how these G2D peaks change. They shift, they change the width, they also change the intensities. So all this is related to the doping level. But if you check literature, the main magnitude that is telling us about doping is the intensity relation between these two peaks. So we can either map that, and if we get a map of this intensity relation, we can see how, for example, for 16 gigapascals, no change, but when you increase 20, 25, 32, 34, 37, there is a constant increase in this change. So if we plot now this intensity relation as a function of the pressure, we can see again that we can precisely control this magnitude with the pressure, and this magnitude as it will be related to the doping. But to see more in detail, to get more quantitative data on the doping level, we also perform scaling probe for microscopy imaging. This is a special mode of AFM, which is an electrical mode in which we can get information of the contact potential difference in our surface. So if now take images of these same modified areas, you can see how again the contrast is changing. If we plot, for example, profiles of this area, we can see that 16 gigapascals, no change in the contact potential difference, but as we increase it, 20, 25, and so on, this contrast is changing. And this constant potential difference variation, we can directly relate it to the change in the Fermi energy level. So we can see that we can control the Fermi energy level very precisely with the pressure. So the Fermi level, we can see from this plot that is shifting towards the valence band. So we are getting a P-doping effect that we can control very precisely locally. Okay. We can, from this data, also can estimate the current concentration variation we get. This is the level of doping. And we can see that for the highest pressures, we can achieve for the order of 1.5 times 10 to the 13 carats per square centimeter, which is a remarkable doping level, compatible with the doping achieved by electrostatic gating, but with advantage that we can do it locally. We can do it just in a specific region and not in the whole graphing sheet based on our device. Okay, so far so good. We saw this effect of the doping, but why was this really happening? Here is where DFT calculations come, and the group of Fernando did some simulations in which we put graphene on top of different configuration of silicon dioxide, mimicking this possible state we have. By doing so, what we found is that if there is just van der Waals attraction between the graphene and the substrate, there will be no charge transfer, there will be no extra doping. They found that there were needed some chemical bonds, even if there is a very low fraction of bonds, but some bonds are needed to have this charge transfer that will feed out the graphene with a Fermi level shift of order of 0.3 electron volts, which is similar, is compatible with what we observe experimentally. Also from the simulations, they can different configurations of the substrate. They found that the pressure needed to start this onset of covalent bonding is between 10 and 20 gigapascals. Again, in very good agreement with what we needed experimentally to start syncing our graphene and start to see this effect. Okay, again, we were very happy. This explained what we observed, but we wanted to see if indeed these bonds were appearing, even if there was a very low fraction. So we prepared some samples to take them to this electrolysis in Trieste, because there the line where we went also had the beam focused to a very narrow diameter, so we can take photoemission spectra from very precise locations. So we can take even images, because it allows also mapping the areas. We can take images of the carbon split, how it's variating in a given area of our sample. So we can see that areas at higher pressures appear in a different color. So we can come now here with our beam and take individual spectra in each of the regions. Here are some examples. What we can see here in a first site is that the pristine peak, which is this one, is now centered in the blue line. But the peaks at higher pressures all are shifted to the right. You see all of them appear at the right of this blue line. So they are shifting toward lower binding energies. This is telling us that Fermi level shift is shifting towards the valence band, as we already knew from KPFM. And also, this is due to this P-doping effect. Okay, nothing new in here now. But if you analyze a bit more in detail these peaks, we can see that peaks for pristine graphene can be fitted with just a single component. Okay, this is the usual thing. But if we analyze in detail peaks for higher pressure, we can see that we need an extra second component to be able to fit to explain these peaks. And this extra second component is compatible with having some carbon atoms bonded to the substrate. So this explains, this confirming what we obtained by the experiment, by the DFT calculations. Just to finish this part, we also tried to find kind of application for this, and we did some modification and studied the transport properties of the modified areas by using conductive AFM. We use metallized tip, we close this circuit, so we can measure the current through this circuit, So we were expecting that in the modified areas, the ones which are lower, which is the ones we have pressed down, since they are p-doped, there are more current concentrations, we were expecting higher current. And this is indeed what we saw. We see an increase in current almost twice the value we had in the pristine graphene. And this is telling us that these areas, the contact resistance between our metal in these areas is lower than in pristine graphene. And this is something quite important because we now go to the take-home messages. I go to the last one before. If we can locally improve this contact resistance with a metal electrode, this means that we can put our metal electrodes in a future graphene device on silicon dioxide and modify the graphene before in order to have a better contact resistance. In that way, we will lower the voltage we need to get the same current. This way, we could get more efficient devices, for example. The other technologies are we were able to locally fabricate areas with tunable p-doping, and we found that chemical bonding is the main responsible for this. Okay, so I will jump now to the other part in which we studied the modification of graphene properties, and in this case, mechanical properties. Okay, so in this case, we studied this kind of devices, which are always, we are also very familiar with in the lab, to study mechanical properties of graphene. We put graphene on top of a hole of silicon dioxide, and in the lab there is a lot of experience of coming with the tip and just push it and study the mechanical response, but also a lot of experience in changing the pressures inside and outside these blisters to then study how these inflate, deflate, and this will also give us information on the mechanical properties. So by doing this, let's say inflation, deflation, we can then study the variation of the height of these blisters with time and obtain characteristic times of decay of these things. Why this is happening indeed? The thing is the holes are not perfectly sealed. Okay, there are some leakage, and in principle there is some controversy in the literature if the leakage is occurring either through the graphene substrate interface or by diffusion in the walls of the silicon dioxide. So we also wanted to try to understand, to know what was the main mechanisms for the diffusion. So we studied, we put graphene on top of many holes. We studied this inflation, deflation time constants of different holes with the distance to the clay, with the size and so on, different configuration of pressures inside and outside the blisters. We also made a kind of simple toy model in which we consider all the leakage going through a cylindrical pipe, just connecting to the closest point of the edge. I mean, this is just to understand what was happening. And basically, from these results, I will not go in detail, but what we can infer is that the leakage was occurring mainly through the graphene substrate interface and not by diffusion. So in order to verify that, we came back to this ultra-high pressure approach, and we decided to study the same blisters before and after sealing, because if we just make something like this in the cartoon, in which we seal an area around the hole with this ultra-high pressure, we will increase in the coupling between graphene and the substrate. So if the molecules are diffusing through the interface, the diffusion will be hampered, and in principle, times should increase. Okay, so we did that. And after that, we can, again, visualize what happens. We have our area sealed, let's say. You see, we have to get these areas like 100 meters below this piping here. So we can study now same blisters before and after sealing. Okay, so we have here the same blister before and after, and we can see that not running now. Let's try to do this here. Okay, it's not running. I know maybe why. Sorry. No. Well, okay, we'll skip it. We'll do the same. Okay, but anyway. Well, it's not working, but basically what happens is that the same blister before and after sealing times it takes like 3 times more time to deflate in this case than was expanded. Okay, if we order. Now it's stuck in here. Oh. Okay. If we now study these characteristic times of inflation deflation at different pressures, at different lists, at different configurations, we can see that after sealing, all the times always go up. And if we go to this model in which we see the effective radius of leakage, we can see that all the effective radius goes down. So this means that we're effectively improving the sealing of these holes, and it's telling us that the main leakage is going through the interface and not through the walls of the wells. Also, we study mechanical properties on this. So we study the indentations on graphene blisters, standard and sealed. And from forced curve indentation, we can get also strain, stress strain maps. And we can see that in the pristine blisters, we can just reach, let's say, a given amount of strain. But when the blister is sealed, we can reach almost double the amount of strain. If we try to push harder, what we see is that wrinkles appear, and there is static behavior in these curves appear. And this is because these wrinkles, the shape is sliding. Okay, it's something like if I have a block on a hole, let's try to do it with the microphone. If I just put in the elastic regime, it will just come back, something like this. Problem. But if I push much harder to this non-elastic regime, it's like this, and we get some wrinkles, okay? Which is what we observe in the image. Okay, so basically, what we see is that by using this sealing approach with the ultra-high pressure, what we can achieve is devices, membranes, that can achieve much more strains than the usual ones. So in summary, for this part, we have been able to improve the leakage rate of this kind of blisters, and also with this, taking advantage of this high graphene substrate interaction, we can make a simple way to improve mechanical devices based on graphene membranes on holes. Okay, this is basically the main facts of scientific results, but there are also long-term implications of this project. So, in fact, it also helped to strengthen and enrich ongoing collaborations we had with previous works with members of the group, such as this one with Fernando and Sergio, which is not specifically here, but also open new lines of stable research between the members of the group. For example, this work is from the times of the beginning of the project. Particularly, these measurements, part of the measurement for this work, were done at the synchrotron in the same beam time when we were doing the measurement for the project. You see, for example, with Enrique García Michel and Pilar, which are well-known experts on synchrotron measurements. Julio and I went there, and as I told you, it was an amazing experience for us. But also, you can see the collaboration continues over the years. This is from last year, and even today, there is the collaboration with the group of Enrique and Julio on these topics. But not also open new lines with people between these groups, this collaborative project, but also with people in the IFIMAC beyond this project. For example, from this project, we started to collaborate also with Julio Palacios in terms of things of 2D materials, and also with SNE and Herco and Pablo García González from C4 and C5 from different studies on 2D materials. But also has opened on things which are still ongoing with people both within and outside IFIMAC. For example, we have used this ultra high pressure thing in part to study, or maybe you cannot see, but there are some ripples in here. This is graphene, and there are some ripples. You can see in the double effect tonicity these 2 points, which is the fingerprint of this periodicity. So we use this ultra high pressure to flatten these areas to help understand the appearance of this rippling. This in collaboration with people from the University of Manchester. We also study, as I told you, when doing this modification, we are modifying the doping level of graphene. So this, in principle, we also modify the optical properties of graphene, the plasmons, how they propagate, and so on. So we are working now on this part with people from Oviedo and Zaragoza to understand what is happening here. Also, Felix Indurain from our department published in 2019 a paper with twisted bilayer graphene, and he found that for a degree of twist of around 5 degrees, and then applying pressure, some magnetism or other exotic effects could appear. So we want to explore this option with Felix, also with the group of Eduardo Liz, who is maybe preparing some samples for us of this kind. And also with Ivan Mirihuelga, who can study electron confinement at the atomic level, we want to try to explore this possible of making different configurations to make some electron confinement and for him to study. So just in summary, so far so good. We have achieved many of the goals we wanted. We have opened many lines of collaboration within the IFIMAC and without. But as Christina mentioned at the beginning, not everything is success and things like that. The main objective of our initial goal has failed. So when all this started, because we saw the carbon phase diagram, okay, and we thought, okay, at room temperature, if I go up to 40 gigapascals, I will turn graphite into diamond. Okay, let's do that, because we can put pure layer graphene on a diamond substrate, get our diamond tip, push beyond these 40 gigapascals, and turn pure layer graphene into diamond. Okay, we will get rich very easy. But this was not the case. We did that. This is pure layer graphene on diamond, and we push it, we lower the areas, and we thought, okay, let's take now IV currents, current transport measurements on pristine regions and modified regions. Since we expected these parts to be diamond is insulating, so we were expecting a huge reduce of the current, but basically the current was the same. So basically we get no diamond. So with this, I just want to finish, and this is still an open question. We don't know what's happening, so we welcome everyone who wants to help us with this to understand what can be happening, because at that time there was also a high impact publication that they claimed that they were able to apply with an IFM tip and convert locally bilayer graphene into diamond-like film. So the data were a bit controversial, so we know what is happening. So this is still, I think, an open question. We can just finish and thank you very much.
So thank you very much, Pablo. I think we have time for some questions.
Pablo, whenever I talk to you guys, you always tell me that you have water all over the place in these experiments. So I was wondering about the usefulness of these DFT calculations, because when you put pressure, probably what you are doing is not expelling the water underneath, and that's the whole thing. No, the thing is, the water is between graphene and the substrate. And in fact, at the beginning, when we found it, we analyzed in detail this the change in height. What we see is that at the beginning, we are expelling part of the water, and part is coming back. But then as we increase pressure, all of the water is coming out, and because of these bonds that appear, it's not able to come back. So at the highest pressures, we have for sure expelled all the water out, and there's no water there.
Thank you very much for this nice talk. I have one question. I mean, you have shown the pressure and the diamond angle cell. So you take two diamonds, you approach them together, and then you get pressure, which is one of the thermodynamic variable. Now, in a diamond angle cell, you have a pressure transmitting medium, which ideally should be as isotropic as possible, and then you can speak on pressure, which is homogeneously applied ideally within your sample. Now, my question, you are more doing a stress experiment, so this pressure, are we using the same word for pressure in your experiments than when we use it in a thermodynamic experiment, I would say?
Yeah, in the case of diamond cell, I have no experience with that kind. So the thing is, our approach is, let's say, quite naive. You see, we just get force, tip. We can control the force. We can estimate. We know the tip radius, so we can estimate the pressure we apply. For sure, the pressure we will apply will be not exactly the one we estimate, because we will need a head model or whatever other model to do this contact area calculation. But in particular, also for this diamond cells, this terapascal I told you is for very special setups with very sharp diamond cells. So it's also not so easy for them to estimate the pressure we apply. So in the end, we're in the same range.
Yeah, but I would say it's more stress, uniaxial stress.
Yeah, in our case, it's uniaxial stress. In that case, it's hydrostatic pressure. Yeah. That's the main difference. They can apply the pressure to the whole sample at the same time. We do it locally with this other approach.
Very nice work, Pablo. I would like to come back to the simulations that Juan was asking you about, because it looks from the images that the bonds that you were forming were preferentially carbon and oxygen. Is that correct?
I don't know exactly.
Yeah, just looking at your images. This is why I'm asking.
Sorry.
This one? Yeah.
Yes. I truth be told, I can't remember. Maybe I'm not remember.
Well, I barely remember. Yes, but it's carbon optic. But the important point here is that there are very few bonds that are necessary to keep the graphene so close to the silicon. And it was a very important and puzzling thing in the experiment, because if you have seen the spectra, you know, the contribution of use in the spectrum XPS was very, very small. So it was kind of contribution. So it was our surprise. And we tried many different configurations, which I remember very well. And only just a few carbon oxygen bonds were able to keep the graphene much closer.
I remember you simulated it. I don't know if it was 100 atoms or 100 by 100, I remember.
Yeah, it was huge.
And in that amount, just if there is one or two atoms only,
yes.
this would account for the
Even less. It was 1%. I mean, I would say 1-2% is like an upper bound.
Yeah, I mean, we will not went further with the simulation because it was completely out of resources. But yeah, less than 1% were enough to explain this charge transfer and the fact that the graphene remained.
That's why you see that basically the same peaks as for fixing graphene. These bonds are less than 1%. Okay. Thank you.
I was going to say that we have time for one question if it comes from a young researcher. So we have a very low participation rate.
Okay, thank you, Pablo, for the talk. I don't know if you are concerned about the kind of the latest work from Elisa Riedo, who said that they achieved this kind of diamond-like configuration with bilayer graphene, and it actually grow.
It's the reference I placed, but if you see the data, for example, there are two sets of data that one of them is more, let's say, I believe it, I can think it's more okay, that they study kind of indentation, they see like the stiffness in the indentations. They study different number of layers, and for example, one layer or 5 layers, they don't see this stiffening, but for, I think it's 2 layers, they see how it stiffens. This could be okay. But then they also do some transport measurements with a function of load, and they say that at some point it stops to conduct, but then it, I mean, not to stop, but conducts less, but then it goes on. And this is quite arguable because you can know there is a effect of the peak with the load you're applying that is changing your conductivity. So that part is the one I know it's not so clear. But in any case, they said that they only achieve that in bilayer graphene. We were expecting, okay, if I have few layers, I push, and at least some of them will let's say bond and will get diamond. We tried, I don't remember if we tried bilayer itself, because at that time, we tried few layers, of course, and we were able to sunk kind of also few nanometers, so it was a really sizable downward of the path, but we didn't find any hint of diamond there.
So I think we have to move for lunch. Last reminder that we have we're all invited for lunch at the Plaza Mayor in the main in el